I understand correctly, there's basically a fork in the road. There's two different general possibilities for our understanding of the universe. There's either the multiverse, which means everything's chaos and we can't understand. We're never going to be able to understand everything because we're only like a compartmentalized universe on our own, and we'll never be able to get any other particles. And then the other fork in the road is called supersymmetry, right?
Yeah.
Can you explain that a little bit better?
Yeah, I mean, I think these are two alternatives that are, I mean, in terms of how we view the universe, we know that our standard model, the theory that we have right now at the most fundamental level of how does the universe work, is called the standard model of particle physics. And it's based on the idea that there's a certain, number of the most elementary particles and certain forces that they interact with, okay? And so there's a finite number of particles, we think. Basically, there's things called quarks, and there's things called leptons. And so the quarks are quarks, and the leptons are things like electrons and muons. And the idea is that these are fundamental. There's nothing smaller. They're not made up of other things. And there are certain fundamental ways that they can interact. They can interact with by magnetic means, which is the way we mostly are familiar with, which is, when particles have charge, that they can form electric currents, they can form magnets. We know that is both electricity and magnetism now are sort of combined, or one force, really. There's something called, gravity, we know, is another fundamental force, that anything that has mass, there's an attraction to it between them. We know that there's something called the weak interaction, which is something that is responsible for the fact that some particles decay. You have radioactivity. So the reason we have radioactivity is particles, there is a certain instability, they decay into other things. So a neutron, for instance, can decay into a proton, an electron, and a neutrino. And then we know that there's something called a strong force, which is understood as a necessity because we know protons are not fundamental particles. Protons are made up of quarks. And so there's something that's holding these quarks together that is very strong, because quarks, they have charge, and they would not stay together necessarily, and they have to be kept very close together. So there's something that's a very, very strong force as well. So we have those four forces: a strong force, the weak force, the radiation force, the electromagnetic force, and gravity. And this has been incredibly successful as a theory. I mean, it explains pretty much every phenomena that we see on Earth. In terms of its accuracy, it's the most accurate theory of science in terms of the scale that it can get down to and the scale that it can get up to. But we know that it's not the end story. We know that there are things it doesn't explain. As soon as you look up into the sky, into the cosmos, there are very big questions we don't understand. We know that there has to be more mass out there than can be accounted for by the particles that we see. We can see that things, essentially galaxies rotating and things like that, we can tell there's something that is gravitationally pulling it, but we don't see it. It's not visible, and so it was given the name dark matter because it's dark. We don't see it. We also see that the universe is expanding. It's not only expanding, it's expanding at a faster and faster rate. It's accelerating. It's expanding at a faster and faster rate. So there's something, we understand that as meaning something in a sense is pushing it. It's almost like it's pushing it out. And we don't understand what that is. And we call that dark energy. We also...
How can we tell that it's expanding faster?
Well, you can tell by when things move away, light, there's something called a Doppler shift. There's a red shift. So it's the phenomena when, for instance, you hear a siren, and a siren approaches, and you hear it as it approaches, the frequency goes up and then comes down, and that it's a shift in frequency, and that happens with light as well. And so stars and various other things, they emit light with certain colors. Okay, I mean, light, different frequencies of light correspond to different colors, and any source of light has a very distinctive pattern of the colors that are in it essentially. And when things are moving away or moving forward, that pattern shifts. And so we can tell by examining the shift how fast something is moving towards you or away from you. And so by doing these detailed spectrographic analyses, they can tell, the speed at which something is moving. And they can tell the things that are further away are moving faster than the things that are closer. Again, looking at examining the time and studying the movements of these things, and studying this this shift, they can get an idea of how fast these things are moving away and how far they are as well. And so, it's incredibly detailed astronomical observations that have really allowed these things. So, we really, yes, it is. How do you tell what's happening that far out? And it's from very detailed spectrographic analysis, really, of the light coming from the light. I'm saying light, it's really electromagnetic radiation, in all its forms. So that includes, X-rays and infrared and visible light and ultraviolet and everything like that. So they look at, they have things that are sensitive to all these different frequencies. So we know that there are these fundamental problems, and there were also fundamental questions about, well, why is the universe the way it is? Why there's a different range in strength of the forces. Okay, gravity is very weak compared to electromagnetic forces, for instance, and you can see that just by the fact that I can just lift up, an object like my glasses, and the forces that I'm using to lift it are basically it's electromagnetic forces. It's that's what allows the arm. It's biological. Movement is contractions of muscles, which are ions moving in the arm. So it's electromagnetic. It's fundamentally electromagnetic. But just little me with my arm lifting this can overcome the entire gravitational attraction of the Earth. So that just gives you an idea of how much weaker gravity is than electromagnetic forces. And similarly, there's a real hierarchy in the strength of the weak and the strong force. And so this is another thing that really was very, very difficult to understand. And there's things in the theory that really don't predict this at all. And there's in terms of the acceleration of the universe as well, we don't understand this. And if you try to do a calculation based on our best understanding, it's humongously off. The calculation is humongously off. It's really one of the worst predictions in science. And so again, this is a question of, well, what are we missing? And what's really interesting is it seems to have a very specific and sensitive value. This value at which the universe is accelerating, what this force is that's pushing it out. Because if it was a little bit more, if the force was, if the force was a little bit more, or or the gravitational force was a little bit less, then, you know, things would never have actually formed. We never would have, you know, after the initial Big Bang, they never would have come back together again. You know, I mean, gravity would not have been strong enough to pull it back together. But if it was too much, then, I mean, if it was too much, then things would not have expanded at all, or it would not be accelerating. So there seems to be this, you know, what we don't understand, that there seems to be a sensitivity and sort of a very specific number that accounts for this balance between a universe that would never form and a universe because it just flew apart, and it would never form because it would just never expand. So there are these various issues, and traditionally in physics, we've tried to understand things in terms of the fewest number of particles, and certain, you know, there's a certain patterns and symmetry. And that has been the approach that has worked up to now. We've seen certain parallels in particles, that they have counterparts to things. And, you know, it's sort of like a right hand has a left hand, and a positive charge has a negative charge, and a spin up has a spin down, and various things like this that have a certain symmetry. And so the hope has been to try to understand any new particles that might be necessary to understand these odd phenomena in terms of the things that we have, that they're related somehow, that they sort of fall into the same theory, and that we just haven't seen them, but there's something that they're going to fall into the same pattern. And again, behind me have this illustration of the standard model of particle physics. It has this very nice symmetrical, round structure. And the hope was that maybe this could be expanded in terms of other symmetries, other parallel things, that would follow the same pattern. And these theories, are called supersymmetry, the idea that there's additional symmetries that we are beyond what we know now, but we could mathematically see that they could work. And mathematically they're allowed, and maybe there's particles that would correspond to that. And so that has been one of the big hopes at the LHC, is that we'd see new particles that would fall into these new patterns, and that could be, part of our theory, our expanded theory. But we haven't seen them. And so, this alternative idea has arisen, is that maybe we're asking the wrong question in a sense. And we shouldn't be asking, why do these numbers have very specific values? The number that determines the expansion of the universe, it's something that's called the cosmological constant. And maybe we shouldn't be asking, for a theory that's going to predict that number, because maybe it's not a special number in general. It's a number that happens to be special in our universe. And so the parallel that's often made is, if you look at the distance the Earth is to the sun, and or any of the planets to the sun, and you could say, well, why is it that distance? I mean, with the Earth in particular, you say, why we have this very particular distance that's just right, that it's not too close where it would be too hot to allow life, and it's not too far where it would be too cold to allow life as we know it. But what we know is that it's not, there's not a theory that says the Earth has to be here. In the aftermath of the Big Bang, I mean, things fell into various distances just because of the way things were exploding and the gravity, and they fell into them. And this one at this distance is the one that allowed life to arise.
It just got lucky.
It just got lucky. But, Mars was not so lucky. Saturn was not so lucky. As far as we know, any of these other ones are not as lucky. And so this has been this wild idea that maybe there are other universes And ours is the lucky one that has this expansion that allowed a universe to form. But there could be other universes where things are not expanding the way they are, where they didn't, or where, you know, maybe it's another universe. You know, it's, of course, it's hard to even say, well, what's another universe even look like? But, you know, say another universe that also had a Big Bang or something, and that the acceleration is different than ours, or that, you know, it's you know, it never expanded the way we're expanding. And so this idea, which is a theory called about that there are multiverses, is a competing scheme, and it's a very different way of looking at the problem, and it's, you know, it's controversial within the physics community, because in some sense, you know, physics has always worked on the precept that we could find a, you know, an ultimate theory that would explain everything. But this is an alternative that's gained more ground in the last, you know, 15, 20 years, especially the last 10 or 15 years, which is basically saying, you know, it's the wrong question to say, how do we predict that number? So it'd be, you know, you'll never predict the number because it's a matter of chance that it came out in this universe that way. You know, there's some support for this idea from other theories. There are theories like string theory that seem to indicate the possibility and maybe necessity of different universe configurations.
String theory?
String theory, yes. Okay. So a string theory is a theory that basically one of the biggest outstanding problems of physics is that the weak, the electromagnetic, the strong interactions are all, in some sense, fundamentally built the same way. There are quantum field theories. They're quantum, really. And gravity is not. Gravity, our best theory of gravity is Einstein's theory of called general relativity, which is a theory of gravity, and it's really just a complete outlier in terms of how it's set up. That it you know, Einstein gave a theory that basically said gravity is because of curvature in our space and time. That it's a very hard thing to picture, but you know, we come up with three-dimensional images of surfaces that are curving, and mathematically, Einstein showed that, you know, if you think of 4 dimensions of, you know, the 3 dimensions of space and time, we can study those things geometrically, mathematically, and the mathematics shows that if you think about curves in space-time, that is completely equivalent to the force of gravity. Because gravity, we know gravity affects anything with mass. And so anything in the universe that has mass, you know, is occupying some space and time. And we can say that if you move, you know, if you bend space and time, things are going to move in a certain way that's gravity. But this is a very, you know, it's completely separate from quantum mechanics. And so, you know, the holy grail of physics in many ways has been to figure out a way to unify quantum mechanics and gravity. And one of the candidates that has been, you know, being worked on now for also quite a number of years is something called string theory, which, you know, in a very simple manner imagines that the little fundamental particles are not like little points, balls, but they're little vibrating strings, and that it's the different frequency vibrations that might correspond to different types of particles, and interactions are the interactions of these things. And, you know, there's hope that this might be a way to unify gravity and quantum mechanics. And there are also indications in string theory that you may need other dimensions. And, it gives some credence to the idea of a multiverse. Again, I mean, these are, none of this is completely proved, but there are overlaps that support it. So I think that has given more weight to the arguments of a multiverse, in the later years, in the last years. But it's still unclear, which way it's going to be. And so experiments like the Large Hadron Collider, so I mean, the big thing with the Large Hadron Collider is that in the standard model of physics, there was, even though the theory worked incredibly well, at the center of it was this thing called the Higgs boson, which was necessary for the theory to work, but had not been seen. And in a sense, the LHC was designed to really determine yes or no if the Higgs existed, and it did. And so in some sense, it was an incredible success. I mean, it was just the ultimate confirmation of, a theory, when you think about it, just this incredibly abstract theory that is incredibly elaborate and accurate and, ultimately explains all of the everyday phenomena we see on Earth. And they found it, with this enormous machine that is mind-boggling, and, the evidence really was convincing that yes, there is this Higgs particle. But so that sort of capped off this nice picture. But then of course it's like, you look outside and there's everything else that's going on, and it didn't. So I think what physicists, they, in some sense, you wanted to find a Higgs, but the real hope is they find something else to sort of start to indicate what is the bigger theory.
What exactly?